Hey, this is Horner, and now we have two students. Oh, this is Rotational Dynamics Free Response Question Review number 2. You have two students attempting to measure the rotational inertia of this wheel. To do it, they attached a string to it, and then they let go to see what it would do. They first want to quantify the motion of the wheel as it falls and rotates, and they want to know what quantity of the wheel's motion can be calculated from the measurements made by students with the equipment provided. So they are given here it says you've got a meter stick, a stopwatch, and a balance. You can find the acceleration, not the velocity or the speed, so you won't be able to do that because it's not going to travel at a constant velocity or speed. So it does have to be acceleration since it is falling and being pulled down by gravity. To do that, we need to measure the time to fall using the stopwatch, and we need to measure the distance from the center of the wheel out to where that string is. The center of the wheel down to the ground. So those are the two things that we are trying to measure. We'll use distance is equal to 1/2 at squared to find acceleration. It is not going to be equal to gravity because there is that rope there. We'll plug the values in for that distance that we measured for it to fall and for the time to fall using the stopwatch. And if you do that, you'll be able to solve for the acceleration. So each of these things, you'll see 1 point for the part I, 2 points for part I, and 1 point for part I. Once the students make the calculation, they proceed to calculate the rotational inertia of the wheel. So on the diagram below, they have the wheel and the string. They want you to draw the forces, not the components that are acting on the wheel. So there's only 1 point here. You need to have both from the attachment point up is Ft. And then from the center of the wheel down is mg. Now they want us to explain how the students can use their measurements in part A along with one or more additional measurements to find that tension. If we find the mass of the wheel, okay, so that would be m, and then solve for the sum of the forces is equal to ma, we should be able to find that tension. So here mg minus Ft is equal to ma, so that is what you would end up doing. Once the tension is determined, so now we can find Ft, because let's just go back up here for a second, and we know that Ft then would be equal to ma, negative Ft would be equal to ma minus mg, so Ft is equal to mg minus ma. Once we know the tension, the students can make one or more additional measurements to determine the rotational inertia of the wheel, state any additional measurements that must be made. So now we've got to measure the radius of the wheel. We had talked about that earlier, but you could do it there, but you really want to put it down here. If you put it up top, you'd have to say, again, according to the first instructions, you would definitely need to find the radius of the wheel. Once you do that, we know that the torque here that is going in a straight direction, so the torque on the wheel itself. So when you pull up on this with a linear force, and you do that and it counteracts this, it makes the wheel turn along this radius. That is the force of tension times the radius, and that will give it a torque, rotational torque, which is I alpha, moment of inertia times the angular acceleration. From that, now we can just go ahead and use angular acceleration is equal to that acceleration we calculated here divided by r. And if you do that, you will end up with what they want in order to find the rotational inertia of the wheel. Other students are given a different wheel shown in the diagram, but they set up an experiment in a similar way. This one has spokes of extremely light, but 8 very heavy masses on it, so you'll see these heavy masses. Those heavy masses can be set different distances. So they've set them at different distances. They've now taken the time to reach the floor and where the masses are, and they've plotted that, and then they did a best fit line. The data indicates that the time to reach the floor increases as the masses are set further out. They want to know, is the evidence consistent with physical principles? Yes, so the further out the masses are, the more rotational inertia. The bigger the rotational inertia, the harder it is to turn the wheel. So as you get those further out, it's harder to turn the wheel as you, and then that just takes more time. So a student looking at that graph says, well, If you use that best fit line, the line is not a very good model for the behavior of the falling wheel, because if you place the masses at the center of the wheel, so if you placed them right here, notice it would take no time for it to fall, and that's not correct. So it's an approximate way of looking at it, but it's not perfect because of this. And that is the end of F2.